Okay, so let's resume. So our second speaker of this morning is Professor Eric Moulines. He's probably known to all of you as a specialist of computational probability, machine learning, signal processing. He's had a very prolific career over very many years. And is a professor at École Polytechnique and also holds a fractional position at MBZ UAI in Abu Dhabi. Amongst the numerous awards and achievements Eric has had is including a former editor-in-chief at the Bernoulli Journal, and he was also awarded the silver medal by CNRS. Eric is going to be talking about Bayesian inverse problems with denoising diffusion model priors. So please take it away, and thank you so much, Eric, for coming to speak here today.
Thanks a lot, Ajay. So it's a pleasure to be there. So normally I'm working on the other side of the Arabic Peninsula. It's the same heat, it's the same type of weather. It's not nicer. It's the same type of weather. Okay, so today we'll speak about, it's a recent project I started. In fact, it's more or less a consequence of a meeting I had in Abu Dhabi 2 years ago, and where people were speaking about inverse problems using deep prior. So it's very, very popular in image processing. And so I started to look at it. And if you look a little bit, if you know a little bit the literature of generative AI, in fact, diffusion models pops up everywhere. So stable diffusion. So, and if you are a probabilist, of course, you immediately want to jump on the problem because there are many, many things that can be done, and both methodologically and also theoretically. I think there are a lot of open problems there. And what I did, in fact, because I am a SMC guy, sequential Monte Carlo guy, so I try to put some sequential Monte Carlo ideas in there. So, and this was really the start of this research project. So it's a research project that I started with a PhD student of Sylvain Lecorf. He's now a postdoc of mine. So he's Yazid Janati. So he's an extremely good guy. Very nice guy and very sharp. And also Gabriel Cardozo, who is finishing his PhD with me. And which makes, so he has no much theoretical contribution, but he did a lot of application of this problem to cardiology. So if you are interested in more applied stuff, I will not have time to cover that, but there are many, many applications on ECG restoration, how to construct an ECG from smartwatch and using this type of idea. And so it's more the work of Gabriel Cardoso. Okay, so I will start very, very slowly. So if I'm too slow, you'll say, okay, you should speed up. Of course, there will be much less math than in the previous talk, so sorry about that. So I will just explain basically what are the principles of generative modeling, and also I will spend some, say, a quarter of an hour to explain what we call diffusion models in this generative AI world. And then the last part of the talk, I will more describe our results on how to apply this type of ideas to Bayesian inverse problems. So what is generative AI first? Generative AI, well, you start, the idea is that you are a big collection of data. So in in all of my talk, I will use images because it's easy to understand. And there have been a lot of work on generative model for AI, for images. But of course, you can apply that to any type of data. As I said, I worked a lot on trajectory prediction. I worked a lot on ECG, so electrocardiogram. And but I take data, I take images to illustrate our finding because it's easier to understand what we're trying to do there. Okay, so you have a very large collection of data. This is a part of taken from ImageNet data set. So it's not. Now it was considered as a huge data set long time ago, 1 million data, 1 million token. Now it's very, very small compared to the type of data set people currently used for diffusion. But yet you can start to obtain rather reasonable. You can start to obtain rather reasonable model out of that. Okay, so you have a large collection of data. Is that what is the objective? Is to define of generative AI is to find a way to sample data which looks like the distribution, the unknown distribution of the data set. So it's generative in the sense that it's not, you are not trying to look at, to construct something like an estimator of the density of this probability density. So it's not an estimation problem, what you are willing to do in generative AI, you are willing to produce an algorithm which is able to generate data which looks like the data that you have used to train the generative AI model. And so, okay, so it's supposedly the data will be very, very complex. So you have, we have a kind of Larsen. So I am the signal processing guy. So I think we should turn down this stuff because otherwise it will annoy you all the time. Or we can put it down, I think, perhaps, or, okay. Okay, so you have very, very complex data set in very large dimension. So typically, on the model I will use, in fact, the model I will use, the data set is in ImageNet, you have images which are something like 200 by 200, so 40,000 times 3 because you have the colors, and even 4 because you have a chromaticity. So it's each observation is something like 10 to the power 5 dimensions. It's huge. Of course, you can use some kind of autoencoders and things like that to reduce the dimension, but typically what you have to take in mind that this is so no you have a lot of data. All of this data are in a space of very large dimension. Okay, and so basically this is a kind of abstract representation of what is the probability distribution, and what you are willing to do, in fact, is you are willing to sample, and this is what I will do later on. So what I will need to do is that so imagine that I have a kind of probability distribution, and a sample of this distribution are simply images, and what I will do today. In fact, at the end of my talk, I will show you how to sample of pi of this distribution conditioned to y. So y can be, for example, something like that. So it's you remove, for example, some part of an image. Okay, you can do what is called outpainting. So you take simply few pixels of the image and you are willing to complete the image. Okay, that's an outpainting problems. You can do some restoration, of course. And there are many, many other type of problem. You can do denoising. You can do deblurring for images, and you can solve the inverse or nonlinear. We can also look at nonlinear problems. I will not speak about nonlinear problems, like what is called dequantization. So you have a JPEG encoded images, and you want to dequantize them, and you can do imaging with Poisson imaging. So low count. So when the image itself is the intensity of Poisson short process. Which happens, for example, when you have image where the photo count, the count of photon are quite low. So we have a lot of nonlinear problems also of that kind. Okay. So basically what we are willing to do is that we will have a kind of generative model, very large dimension, and you are willing to sample. So we will want to solve some kind of Bayesian inverse problem. And the Bayesian inverse problem is how to sample this very large distribution conditioned to some observation, okay, with application to ear images. Okay, so first, the first thing to do is how to construct this model for parametric model for the data set and what for the data. So pi data is not known, of course, but you simply know the distribution. And what we will do is that we will fit a generative model for this, and the generative model is simply a kind of huge deep net with a huge number of parameters, p theta, but basically it's a parametric model. And the way to fit the parameter of this data is simply to look to perform some kind of likelihood function estimation. So it's some form of maximum likelihood. It's not exactly this. I will explain later. So in fact, you don't do exactly. It's more or less like maximum likelihood, but you do some kind of. You will see some kind of what is called evidence overbound optimization. So you will do it, but we carry out this optimization in a kind of variational sense. You will feed the parameter, okay, and then starting from that, you will add the potential function. So in the case of an inverse problem, the potential function will be the likelihood of the observation, which can be computed from the when you know the inverse problems that you are tackling, and you are willing to sample this particular distribution. So what makes it complicated is that, of course, this prior can be very complicated. Sometimes you don't even know really the distribution of the prior. I will explain why. So when you do typically in the problems that we have, we don't have an expression for the density, so you cannot really use this condition. And so you have a lot of problems to solve in order to implement this program. Okay, so I will start by presenting rapidly what are denoising diffusion models. Who are aware of raise hand? So you are all aware? No, you are not aware. Only few people. So I will spend some time. It's funny. That's funny because it's math which are easy and which are spectacular. So there are no much in math in general. It's not spectacular or it's not easy. Okay, here it's easy and spectacular. So it's good. Only when I was doing, as I mentioned, signal processing, it's like information theory. Information theory, you take the cover in Thomas' book, the math are super easy to understand, and you have a nice result at each chapter. That's perfect. So it's exactly the same there. Okay, so what you do in diffusion model? So diffusion model it's fantastic. The idea comes from many fathers, so it's difficult to attribute, but it started at the beginning of 2010. And it was not very successful initially, so it's a work by Ivarinen. So if you're the very first person working on this type of ideas, Ivarinen. So, and the funny thing is that Ivarinen was a postdoc of mine in Paris in 1998. He has a big career now in Finland. He's still in the academia. When you see the level of this guy, it's a kind of miracle. So it is still in academia. He's a very nice guy. And so he makes the first steps, and then a student of Yoshua Bengio called Vincent, so did the second step, not very successful. And the whole idea, in fact, and the formalization come by a guy which is really a genius, which is Sasha Schordikstein, so he did a lot. And I think he has this terrific idea, but of course it's not out of nowhere, of course. And of course, if you know sequential Monte Carlo's idea, of course, you will recognize bits of things which have been there before. Okay, so the idea is simple. What you do, and I will present it first in discrete time, and then we move to continuous time later. Continuous time is not essential, I think. It's called diffusion because people think that it is fancy, it makes a bit more, it's exciting, but in fact, there is no, I think you can stay in discrete time, in fact, without, so it does not help much to go to continuous time, I would say. Okay, so what you do first, the first thing that you do is that, no, why just say that? Okay, I will, sorry about this, I will. It's not the best time, or no, we don't know why. It's the best time. Okay, so you will not be annoyed anymore. Okay, so you have a forward chain, and the forward chain, what you will do simply is that you add data to the observation. Okay, typically you add the Gaussian noise, so you can do something else, of course, but you typically in the original application, what you do is simply add data. So you add data to the observation. That's a forward Markov chain. And then what you will do, and so the idea of the forward Markov chain is really undesigned. And the idea is that you start from the distribution of data. By data, you add noise until the time that you get to a kind of target measure, which will be the reference measure, which is most often in this type of application taken to be a Gaussian. Of course, it can be something else. Of course, it can be, so in the theory, nothing prevents to go to target something else than a Gaussian distribution. So that's the forward process. And then what you will do is that you will learn the elements to make it backwards. So the thing which is important is that you will run the process backward in time, and the generative process will come backwards. So you will start from the reference distribution there, and then you will run the backward chain, okay? And the backward chain will revert you to the original data by data. Okay, so the whole process is, so you have two things to understand, is that in the forward process, you will learn more or less how to construct the backward chain. And once the backward chain is there, what you will do is that you will pick a point according to the reference measure, and then you will run the backward chain, the backward Markov chain, so backward in time in order to sample points from the original distribution by data. So it's fantastically simple. And so we'll make it a little bit more concrete. Okay, so you start. So sorry about the notation. It's really a kind of mix of notation used in machine learning. In machine learning, there is some kind of allergy to measure theoretical notation. So it's funny because it's like a SMC. I was in signal processing. In signal processing, people did a lot of SMC, but you cannot use direct measure. Okay, so you can do filtering on Riemannian manifold and things very complicated, but only with density notation. Even Arnaud Doucet at the beginning, so you have delta functions all the time, something like that. Okay, I'm tired. I'm too old to start to fight. Okay, so I was adopted some kind of notation which are a mix between mathematics and non-mathematical notation. Okay, so but it's not a big deal there. Okay, what you do? Okay, forward chain. You start from the initial distribution, which is pi data, which has denoted Q naught, and then what you do, you define a kind of non-homogeneous, apparently Markov transition kernel, which would be Qt Tt minus 1. So which you start from xt minus 1 and you end up in xt. So of course it's a non-homogeneous Markov chain. The joint distribution of x1 xt. T is the number of time steps that you perform. Condition to x0 is simply the product of this Markov kernel. These Markov kernel are completely uncrafted. You define them. In general, they are very, very simple. And what they do is that they transform the original distribution into a tractable reference distribution. Okay, if you stay to simple example, and I think is by far the most common example in diffusion, of course, you can imagine things which are more different. You simply use as a Markov, as a forward kernel, you simply use an autoregressive kernel, so which means that the law of xt is conditional to xt minus 1 is simply a Gaussian with mean which is 1 or the square root of beta t of xt minus 1 plus beta t I. So it's called it's variance preserving. It's called variance preserving transformation. You can there are other techniques which are variance exploding. So it's one possible choice. Okay, so you apply this. And of course, it's because it's very, very simple. So you can compute in particular the distribution of xt given x0, okay, because it's Gaussian. So it's simply t step of an autoregressive process. So when you have t step on an autoregressive process, you remain autoregressive. And then you will see that the dependence of initial condition is in x0s, which now affected by this product alpha bar t. Alpha bar t is a product of the alpha s, which are 1 minus beta s. And of course, the noise is 1 minus alpha bar t. So what we typically do is that you choose the sequence beta t in such a way that alpha bar big T at the end of the day is equal to 0. Okay, so it's can make it constant. It's in general not a good idea. It's not very well understood how to choose it optimally. So of course, it could be data dependent somehow. There are some that typically something that people start to look at. It's important. In fact, the design of this beta t and alpha t is important, and it's kind of hyperparameters which are chosen by some kind of rule of thumb. But provided that alpha bar t at the end of the day, when t is the number of time steps is equal to 0, then xt is almost a Gaussian distribution that will be your reference distribution. Okay. Okay, so that's the forward process. Very, very simple. You apply, in fact, to xt, you apply simply a kind of linear autoregressive process, even with completely diagonal coefficient. And now, so to generate a data sample, you need to start from the reference measure, and then you have to gradually remove noise by running a Markov chain, backward Markov chain. So you run Markov chain backward in time this time, and of course this Markov chain should be learned. And I will explain how to learn this Markov chain now. So what do we define? We define a backward in time kernel, so which is indexed by theta t, theta, so which is p theta of theta minus t minus 1 t. So you are backward in time, so you condition to xt, you go to xt minus 1. And what you will do, I also take a Gaussian kernel, but this time this Gaussian kernel will have a mean, which is the mean is dependent upon theta t, and it has some covariance. So there today I will make a very simple choice. So I will take a kind of very, very simple covariance matrix, diagonal one, by the way. But in general, you can make it a little bit more complicated, and you can take sigma t or theta of xt and these two means and covariance matrix are typically parameterized by deep neural nets, typically UNet. So it's like, for example, for ImageNet, you have the number of parameters which is needed is typically something like 10 millions. So that it's not huge. It's not for ImageNet, the models are not small, so it's not 2 parameters. It's not nothing compared to, for example, Llama 2 or these big LLM models. But it's large, but not super large. Okay, so imagine that you know how to sample, so you know this parameter, and the way you will generate data, so really this is the generative process. You will sample xt from pyref, and then you sample backward in time according to this learned Markov kernel. Is that okay? Everything fine? No, now I will explain. And so that's the expression. You will see how the score comes into play, but much later. Data, you take the data, you destruct the data, you destruct the data structure by adding noise, and then at the end of the day, you start with noise, and then you go back to the data. Okay, so how to learn this distribution? So it's as I said, I start with a variational approach, which is due to O and sync, and the idea is the following. So what you do is that okay, so you get this P0 theta, X0 dxt. So you start with pyref and it's backward kernel, so that's a joint distribution of X0 xt. And what you are willing to match, in fact, you are willing to match the distribution, which is a forward distribution, which is known. Okay. And what you will typically do is that you will see, in fact, Q1t given 0, you will see it, in fact, as a kind of variational approximation of P theta. So it's funny, but you do a variational approach. So it's, and so which means that it's classical in variational methods, and so it's called elbow. So I write it, it's minus elbow if you wish, because it's elbow is an evidence lower bound, so it's now minus elbow is an evidence upper bound. It's an evidence upper bound. It's a U-bow. I will call it a U-bow evidence upper bound. So it's simple consequence of Jensen inequality. What you will maximize, instead of maximizing what would be the likelihood function written there. So you will not look at the likelihood function. You will minimize this criterion. Okay, it's not exactly the same. Of course, there is some discrepancy. It's a lower bound, and it's typical when you do. It's exactly this type of method that you fit when you fit a lower bound in variational approximation methods. Okay, so you write it, you can expand. Of course, doing this, so it gives you a first criterion, and of course, what you will typically do is that you will a little bit. You can simply integrate this quantity. So you can simply integrate this quantity and obtain by Monte Carlo. And typically with sample, you can obtain, but it will be very, very noisy. So you do something a little bit different. And the thing which is different is a kind of Rao-Blackwellized version of that, which is basically the same. So what you start to do, in fact, is what you start to do is that you take, in fact, the conditional distribution of Q1t is 0, so the forward chain. Okay, which is given by that, and you might decompose it, in fact, as a product of backward chain. So you make the backward decomposition of the forward measure. Of course, because it's a Gaussian distribution, everyone is Gaussian there. All this Markov transition Qt minus 1t are also Gaussian. They have completely explicit expression. So you simply have to compute means and covariance, and you will obtain exactly the expression for this kernel. And it's exactly another representation of x1t given x0. Okay? And you write exactly the same U-bow, evidence upper bound, minus elbow, and you obtain this, in such case, this relation, okay? And then this time you integrate, and because everybody there is Gaussian, okay, you have to integrate, and you have to compute all this quantity, which are basically the KL. So it's here you have the KL between PT and Qt0. Here you have the KL between PT minus 1t of xt minus 1 with respect to Qt minus 1t 0, and that you integrate, in fact, you integrate this quantity with respect to Q0t, okay? Okay, and you see that all this, so it's kind of really a Blackwellization. You see there that all this quantity does not depend upon trajectory, but it simply depends upon the pair xt x0. Okay, so you can go even a step further in the sense that you can, as I promised, you can compute this backward kernel, so t minus 1, some bridge if you wish, xt minus 1 given xt x0. They are Gaussian, they have constant mean. The constant variance, which is nice, so which is given there. That's the constant variance of these bridges. beta tilde t is also completely explicit, no real surprise, so you are in a Gaussian world, so the variance doesn't depend upon xt, so perfectly nice. So what you will do, so typically you will fit, so instead of fitting sigma t, you will technically fit by beta tilde t identity. That it's not necessarily a good idea to do that, but in fact, to make things simple, I will simply keep that as a condition. And what I will have to minimize, in fact, the conditional KL, so of xt minus 1 given xt x0. And because I match the KL of two Gaussian distribution with the same variance and different mean, the KL can be simply written as a difference of the square difference, the norm of the difference between the two means. And the thing which is funny there is you look at that. So in the backward bridges, the backward bridges depends upon xt and x0. Okay, and so what typically I need to do, I will need to simply have when I do the minimization, what I simply have to do, I have simply to predict, in fact, x0. Okay, so it's written there. So I simply substitute. When I simply substitute the expression of mu tilde t, it's not a big surprise. I simply to predict, in fact, x0 according to xt. So in fact, the thing which is funny is that when you write this evidence upper bounds, and if you just use the backward decomposition of the forward measure, but you end up with a simple problem to solve. In fact, you have a simple problem to solve, which is written there. So the evidence upper bound is given by this quantity, okay? And this quantity, in fact, what you have to do, it amounts to solve, you are willing to predict x0, the value at x0, given that you are at xt. And you do that, so xt, you know exactly the law of xt. The law of xt is x0 plus some epsilon, because you have used this Gaussian measure. So in fact, you simply have to pick the way you will approximate this expectation, that you will pick points in your data set. So you have sample from Q0, so it's sample from P data. You pick point from the data set. You simply add noise, some noise epsilon from a standard Gaussian distribution. That gives you compute the square root of alpha t x0 plus 1 square root of 1 minus alpha bar t of epsilon. You minimize the norm in terms of theta. And so you have a kind of Monte Carlo approximation of this quantity. And using this Monte Carlo approximation of this quantity, you end up with an estimate of the parameter. So this is called a denoising score matching criterion, and I will explain why it is a score, but a little bit later on. Okay, so if you rewrite stuff, so you know exactly what is the expression of mu t of xt given x0 and xt. So it's given by this quantity. So x0 can be expressed in terms of xt. So if you just parameterize x0 t theta in terms of with epsilon at t 0t, which is in fact the noise predictor. If you are willing to predict the noise. In fact, and this is exactly what we are doing in practice. When you are doing practice, you are trying to predict what noise has been added. So what I do, I observe xt. Xt is x0 plus some noise, some Gaussian noise, and so given the pair xt x0, I am trying to predict what is the amount given xt, of course. I am willing to predict what is x0. So it's really the denoising. So you are willing to predict the noise. So I give you xt, and you are willing to predict the noise which has been added to the data given x0. Okay, so it's exactly the denoising criteria. Okay, so you can interpret that in continuous time, and this is where the score, and so Alex will be much more interested. It's so much more fun. So it's completely useless there, I think, but more fun. And they use a lot of this continuous time formulation, I think, to impress the non-mathematician crowd. Okay, I don't think it's super useful there, but why not? Okay, so what is the continuous time formulation of these ideas? Continuous time formulation, and this is why when you look at the web, you will find denoising diffusion. So there is diffusion somewhere. So it's the same idea. So you have Q0, which is distributed according to the data distribution, and you denote by Qt the marginal distribution of the diffusion at time t. Okay, and you will run a diffusion which which is ergodic and which go to some a measure which is called pi-ref, say for example standard Gaussian distribution. So the one obvious choice is to use an Ornstein-Uhlenbeck diffusion, so constant drift, constant diffusion term, so dxt equal minus 1/2 xt dt plus dwt. Okay, why not? And then you know that the Ornstein-Uhlenbeck diffusion is reversible, so with respect to pi-ref, which means it's also perfectly ergodic. You can also express what is the joint distribution of x. Of the kernel, all the kernel are completely explicit there, so it's the magic of Ornstein-Uhlenbeck diffusion. Okay, so you can exactly express what is fs of xy. And what you will do is that you will typically compute the time reversal of the diffusion. So x with the right arrow is the time reverse version of the diffusion. So more or less, it should have the same distribution that xt minus s. Okay. And what has been shown, in fact, is completely non-trivial. I will spend 2 slides to explain why. Is that in fact there is a reversal to this diffusion, which is also a diffusion, so in some weak sense. So of course, I will not give us the details there, but you can express the reversal as a diffusion in some weak sense, and the diffusion is written there. So it's dxt, it's 1/2 of xt dt plus the gradient of log of qt minus t of xt dt plus dbt. Okay, where b is of course another Gaussian process, and of course, what is log of qt? If you remember the notation, qt is the law of the forward diffusion at time t. Okay, so which means that this means that what you have to learn, in fact, is the score. Okay, the gradient of log of qt minus t. You have to learn the score of this diffusion. Okay, and this has been proven. So there are papers. The first paper, in fact, is funnily enough, is of time reversal of diffusion. Is an Australian guy. It's BDO Anderson, which is very, very famous in control theory. So it's you know him, no? Yeah, he's very, very famous in control theory. It's the father of control theory in Australia. Not later. So I think that there are some. It's really proof for engineers. I think it's not completely. So in fact, the mathematicians. So the first mathematical results are done by Etienne Pardou and one of his PhD students, Osman, in '86. And then around '86, there was a lot of papers on time reversal of diffusion using different arguments, Maliaven calculus and things like that. And I will explain that a little bit later. Okay, so there's a whole theory, and if you are really interested in mathematics, there is a very nice paper written recently by Catio, Giovanni Conforti, Ivan Gentil, and Christian Leonard, on which is a kind of survey paper explaining all this reversal of diffusion problems. Okay, so you start with the diffusion. So in the forward sense, you simply have to run Ornstein-Uhlenbeck. It's not very complicated. In backward sense, you need to learn basically. So you will run the diffusion in backward sense, but before doing this, you need to approximate, in fact, the score, which is the gradient of log of qt of x. The same, you will compute the score, you will approximate the score, so the score will be a function which will depend upon some parameter theta. And there is a formula which is called the 3D formula, so it's not Richard 3D, it's another 3D formula. So the 3D formula give you exactly an expression for the score. It says that the score, in fact, is given by this quantity. Okay, it's x minus alpha t x at 0 of x t sigma t square. It's a very easy, in fact, that's a very easy calculation. You can try a good exercise, so it's not difficult to guess. And where x0, xt is simply the conditional expectation of xt given x. And it's funny because it's exactly the type of criterion that you solved before. So for completely different arguments, but you solved exactly the same denoising problem. Okay, so which means basically what you need to work. You need, in fact, to learn, in fact, how to run this problem. To run this problem, what you need to learn this conditional expectation. To learn this conditional expectation, you need to learn a conditional. You need to solve the conditional expectation as an optimization problem. So you need to learn this function, the function x hat of 0t, and because it's a conditional expectation, because the score depends upon the conditional expectation, you simply solve this type of problem, which is why before, because I call that the score matching loss. Okay. And you obtain, in fact, this, what you say. So in general, so I will not spend time on that. In general, you can revert, in fact, all diffusion. So if you take a general diffusion, so BT, YT dt equals sigma T YT dBT. So typically, there is a general expression, okay? Formally, you can find the general expression for the diffusion, which is given there. Okay, it's easy to check that when A, which is sigma theta transpose, is equal to identity, there are some terms which vanishes. So it's this term vanish typically. So which make it much more easier to handle. Okay. So it's exactly what happens. So AT minus T becomes a constant. Then if your AT is equal identity, if you take a constant diffusion term, so it will be a grad of log. It's a score function, and if you take BT equal 1/2, it's a constant term, so you end up exactly with the same type of IDs. So of course, in fact, as I said, it's not completely straightforward. It's completely straightforward in discrete time, but it's not completely straightforward in continuous time because the time reversal of semi-martingale is not necessarily a semi-martingale. So in fact, you need to be careful. So you need to assume that beta is locally Lipschitz. And is bounded away from 0, and that the derivative of this quantity is controlled in the sense of diffusion locally. So if you look at the Osman and Pardue paper, it's very painful to read. It takes a PDE approach, so you have to know a lot of PDEs in order to understand how it works. There are some results, more recent results, which relax some of the condition of Pardue, which takes a completely different approach by Malev and Calculus. And there are some, in fact, there is a paper which is easier to read, so which is due to this paper, which is due to Hans Vollmer, so which is devoted to the case where the diffusion term is equal to a constant there. And in that case, of course, it proves under a condition which is called a finite entropy condition. Okay, so it assumes that there is a finite entropy condition for BT. It proves, in fact, basically the general reversal formula where BT star is equal, so you have the same formula, but which in that case can be used in more general cases. Okay. Okay, so that was just to say that there are some math behind this, and so, but basically what you do is that you learn, so you have to learn, so I remember, so you take points on V0, you add noise, okay? During the noising process, you will learn, so you perform a diffusion. During the all this step, what you are trying to do is that you are learning the score function. And when you are running backward in time, you are denoising and you are sampling the observations. Okay, now I will just explain how this can be, how we can use this type of IDs to for sampling a Bayesian problem. So here, to make things simple, so I will concentrate on Bayesian linear inverse problems. So I have an observation Y, okay, which is given by a given operator A, which is assumed to be known. So of course, it can also depend upon some parameters, but it's not very difficult. And then I add some noise. Okay, so it's a simple Bayesian inverse problem. But what I assume is that X is given as a prior of P0. So X is generated according to the diffusion. Okay, and if you remember well, in fact, what I did before, in fact, I have a very simple way I learned the score. So I have a very simple way to learn the diffusion backward in time, but I don't have really an expression of P0. Okay, P0, I don't have an expression for the density. So it's I can compute, but the expression of the density, I need to integrate a Fokker-Planck equation. I am dimension 40,000, so it's a bit hopeless, so I will not do that, okay? So what I want to do, I want to sample, in fact, so I will use the diffusion priors that I've learned, for example, on ImageNet, and I will apply my operator, and I want to compute this posterior sample using a diffusion model. Okay, so how it can be written formally? But okay, so I know what is P0. P0 is the marginal of this distribution, so I just drop, in fact, the theta. So the theta is what I have learned before. So it's a parameter theta. The theta are in this backward kernel, and I just add a potential I times 0. Okay, so it's a bit strange in the sense that everything is written backward in time, but basically it's a Feynman-Kac formula. It's a Feynman-Kac formula, but which is very, very specific in the sense that this Feynman-Kac formula, all the potential are null, exceptionally one. So it's exactly like if so it should be, because I should have. Some people now start to say, okay, now I have the diffusion model, and I just put it forward in time because it's like when we go backward, it's always for us more complicated than going forward. But it's exactly like if you have, imagine that you have the problem is the following. You have a diffusion, okay, that you know, even say constant diffusion term, and you simply add the potential. You know that this diffusion has some kind of distribution at time t, okay? And you add the potential on this distribution at time t, and you are willing to sample this distribution pi of the diffusion at time t multiplied by this potential and renormalize. It's exactly the problem that we have to solve. Okay. Okay, so this is why I started to be interested in this type of problem. And of course, we know a lot on sequential Monte Carlo. You are students of Agile, so you should have been exposed to sequential Monte Carlo, I guess, some of you at least. At least all the postdocs of Agile should have been exposed to sequential Monte Carlo. So of course, starting from this formula, you can simply define what are called backward functions. So backward functions are not completely explicit, but they are given by this. So the backward function is G0y, so it's a potential at time 0 multiplied by P0k of dx0xk. So be careful, I can give this expression, but I can sample from this quantity, but I don't, it's a bit complicated. There is no, so this backward function need to be approximated somehow. I will see that later. So it's easy to see that this backward function satisfies this type of recursion. So it's when you know the smoothing formula in Feynman-Kac, everything becomes very easy. And you define in such a way, you define this kernel which are twisted by the observation. And the kernel which are twisted by the observation is simply the forward kernel, so which is here the backward kernel, because we are backward in time, and that which are divided by the ratio of these two backward functions. So it's called it's a backward decomposition of it's called the forward smoothing decomposition, but here it's a bit misleading because we write this forward smoothing decomposition by using the backward kernels. Okay, and basically it's very easy to check. It's very easy to check that what you will do, in fact, basically that the same. In fact, you start with the Feynman-Kac formula there. Okay. You introduce this decomposition and you obtain something which is smart in the sense that this Feynman-Kac measure now becomes like you take a measure, of course, which is not normalized. So it's not an initial measure, it's Pn dxn, which is a reference measure that you multiply by this backward function, beta 0 n of y of xn, renormalized by the normalizing constant zy. And then you simply have to propagate this backward measure through kernels, which are themselves altered by the backward function. Okay, and if you look at all the results, so it's not written like that, but if you look at all the results which have been which appeared essentially last year, this is why I start to be interested in this work last year. So I started 2022 because I saw the first paper popping up at that time, and many papers have appeared since then on this topic. So by Chung, Song, which is a big name in diffusion, Bill Tripp, he was a student of Arnaud Doucet. Arnaud Doucet did a lot, of course. and many of them, Wu, Zhang, Boyce, and people. So, as I said, the usual SMC crowd plus newcomers from machine learning. Okay, they all more or less do that. Not necessarily, it's not exactly expressed like this, but you find, but of course, as I said, it's not as easy as it looks because all these backward function beta are not explicitly known, so you need to approximate them. Okay, so I will not discuss all this approximation because it's a bit complicated. So one of the approximation which has been suggested by Song and which has been used by many others is simply to use, in fact, what is called the backward. This approximation of the backward kernel. What you simply do is that you simply plug, in fact, in the backward function. So if you remember the way we have defined the backward functions are the bridge, okay, in which normally when you don't condition with respect to y, you plug in the bridge, in fact, the conditional expectation of x0 given xk plus 1, and if you just massage a little bit the equation, you see that in the same type of approximation, you have to substitute it with a bridge with a conditional expectation of x0 given xk plus 1 and y. And the observation, okay? So in fact, this conditional expectation is given by this quantity. Okay? As I said, in fact, you more or less know how to sample, but not you more or less know how to sample from this quantity, but it's not really an easy task. But you don't know how to approximate. So you will need at some point even to. This is not a quantity which can be computed, so you need also to make some approximations there. Okay, if you look at the 3D formula, so the 3D formula that I used before, you can express this conditional expectation in terms of the score, okay, of pk. So when you look at the score of pk is given by p0y. So p0y is simply, so I drop the normalizing constant, is the potential at time 0 multiplied by the distribution P0, okay, P naught, and which is propagated by QK0 by the forward kernel. Okay. Okay, but now you have what you have there. So you have P0, you have QK0 of xk x0, but this is a joint distribution IO of x0 and xk, and assuming that the backward kernel is a correct approximation of the forward kernel, this is approximately equal to P0k of dx0 xk of pk xk, okay? And it means what? It means that now if you take the log of this quantity, the log of this quantity become exactly the log because you have pk of xk. So the gradient of the log, you have the gradient of the log of pk of xk, but this is exactly the score function of the original model. And then you have the gradient of the log of this backward function. Okay? Good. So what people have suggested is to use, so you simply use a pre-trained approximation. So what you simply do, in fact, so of course you have to estimate this backward function, and Song, in fact, make a very, very simple approximation. He say, okay, so I simply, for the backward function, which is where you have to integrate the potential G0y with respect to the distribution of P0 y of x0 given xk, what you simply plug, in fact, this approximation there, okay, and you obtain what is called DPS, which is diffusion posterior sampling, which is, I think, the most cited paper in this area. Of course, it's incorrect because there are two approximations there. And in practice, in fact, it works, but you have to be careful in the sense that the choice of this kernel is the choice of this parameter gamma k it's quite sensitive. But yet it's yet algorithm that is used most often. So there are other approximations that has been done. So for example, Song make an approximation where instead of approximating the backward function by plugging the x at 0 in the potential, he use a kind of Gaussian approximation. So you have the same idea has been developed by Resch and his co-author. So there are many ideas in this area. So other approximation and other way to do this. Okay. So boys working with Jacola and Tripp did something else. He did a kind of variational approximation of this quantity. So what we did, in fact, our first paper was to make a plane, something which is more Feynman-like. Instead of using all this approximation of the optimal decomposition, we use a plane approximation, and we call that Monte Carlo wider diffusion. So what we did, in fact, is that we say, okay, we have to start with, we will introduce, in fact, artificial potential, Gn of gk of y, of course, that we choose. Okay, this time there are no approximation for this potential. And in fact, you can rewrite, in fact, the Feynman-like model as this product. So you have a product of ratio, of course, it will be exactly equal to G0. So the potential does not modify, in fact, the backward process. And of course, the idea there is that you have this G0, and then you introduce a sequence of potential, and this potential will guide, in fact, backward sampling. Okay, and basically what we will do is that we will apply to this potential the classical SMC recipe. So starting with an approximation of pk plus 1y with particles, we make an approximation of pkyx, okay? And gradually, with this population of particles, we will build an approximation of p0y, okay? As I said, the choice of this guiding potential, of course, is crucial. In fact, it's not, we have a kind of general recipe to choose them, so it's not very, very difficult in practice, especially for linear inverse problems. So I don't have time to explain, but we have a general recipe to choose potential, which works quite well. But otherwise, once you have chosen this, in fact, this choice of potential is a bit irrelevant in the sense that it's simply a way to help it's not like the other approximations which are done in the diffusion posterior sampling, because in fact the formula is okay, whatever the choice of the potential are. Of course, in practice, you need to have potential which guide efficiently the distribution of particles. Okay, so you start, so it's a standard SMC technique. You have a population of particles, so I use you simply backpropagate this population of particles. You compute weights. You assume that this weight can be computed explicitly because you take Gaussian potential. This is also Gaussian, so you make these quantities, these weights are completely explicit. And then you simply run your particle by selecting this particle according to this weight, and you obtain an approximation. You run backward in time like this, and you obtain at the end of the day an approximation of the target distribution. As a potential, what you need to do typically is that you will simply take, and I will a bit complicated now to explain why, but we simply take, in fact, a Gaussian potential, which are with a mean which is square root of alpha k y. In fact, you can place here, and some variance. No, I take this one, but it's not necessarily the right variance. So it's the thing which is interesting is that you need to. So the potential gradually you integrate observation. In fact, you integrate observation in basically the same way you have noise, because the observation there is a bar alpha bar k. So it's the same way you have add the noise to the to xk before. Okay, so that's the potential that you use, and in all the experiments that we do this potential. Okay, so that gives you exactly what are the potentials. That's the backward kernels that we use, and we use a classical sequential Monte Carlo method to sample our distribution. So I think I have some examples there on the Gaussian mixture. So it's 2D, so it's not very complicated. So we have so it's a Gaussian mixture. So P0 is a Gaussian mixture, and what the green, and we look. What I'm really interested, I am interested in conditioning with respect to one particle. So it's a kind of in painting. So I have a distribution with two parameters. Okay, so x1 it's a bidimensional distribution. I simply I freeze one dimension, and I'm willing to sample the distribution of x given y. Okay. Okay, so I just fix this value, and I want to fix this quantity. Okay, and I learned the diffusion. So for the diffusion, the score, if you look at the score function for a diffusion, So the good thing with Gaussian is Gaussian remains Gaussian. So it's good. So the mixture of Gaussian remains a mixture of Gaussian when you have noise. And so you can learn explicitly the score. So the score is not even, is a completely, the score there is approximated with no error because we use the exact score. Okay, so that's the population of the particles at time 450. That's my particles. And you see, so I draw them backward in time. So according to my Feynman-Craig formula, so I just propagate the particle, I resample every time. And you will see that you will see the population of particles which evolved and sample exactly the distribution. And so we did that. We did the same stuff with Gaussian, and we do. If you look at even in quite large dimension, we do much better in terms of. I think it's what we report is slice assertion distance between the posterior distribution. For I think it's a 25 Gaussian. And the same for rotated funnel. And so we look at the distance. So we look at the distance with respect to the true target, okay, which is obtained by a gigantic MCMC procedure by slice assertion distance. And you will see that compared to all the technique which has been reported so far, like DDRM, DPS, RNVP, so which is another method, we are doing much better in terms of accuracy, especially even in large dimensions. So the accuracy is much better there, okay? Everything makes sense. So if you integrate your condition, so you are on dimension 100, 800, your condition with respect to 4 samples, and you will see that DPS is quite biased. In fact, there is some bias, which has not really been well characterized. And you have to be very careful because people in general use DPS, whereas DPS what we observe is that DPS is, you are not sampling the posterior, you are sampling something which looks like the prior, which is slightly different from the prior, but it's not exactly the posterior. Okay, so that's exactly, so another experiment where we show that DPS, for example, is keep too much the prior, okay, it's on the 25 Gaussian experiment. So we are doing perfect, RNVP is stuck in modes, and DDRM is not bad, but DDRM keeps too much of this prior distribution. This is typically what people observed. Okay, so that example, super resolution examples. So what that the samples, okay, that ground truth, okay, that's ground truth. That the observation you simply lower the revolution. And then that's the sample as they are reconstructed. Okay, so you look at according to different techniques. Okay, so you will see that the MCGDIF is doing quite well there. But okay, so that's another deblurring example. So in the blur, you add you take the original image, you add blur and noise. Okay, so blur is you have a blurring operator there, and then that's the image which are reconstructed. With so on different data sets, so that celeb, that church, bedroom, cats, flowers, and cipher. So we have the same for ImageNet, of course. And that in painting examples, so where you simply remove part of the image and you try to reconstruct the whole image. Okay, so I'm running out of time, so we don't have time, and I think we already said much. I will just show you now our last method, which works much better than. So where we combine, in fact, DPS ID and particle filter. And just to see, we show you the same type of image, but we need another hour to express this thing, and you don't have, you are not. And so that's, for example, super resolution example. So we look at what, so it says the original image, that's the observation, okay? And that's what we obtain with DCPS. So it's much better than SMC. So it's we use SMC. There are some SMC steps inside, but we use SMC in a different way. So you observe this, okay, and that's the samples that you're constructing, okay. That with DPS, which is, you know, it works well, DDRM. So that's the same type of ID. So it's funny because you can reconstruct. It's really Bayesian in the sense that you have, of course, you lose some information. So you have many visages. Which are compatible with this observation. This is what we see there. The same for castles. the same for, so we show in painting images, that's in painting of image, not super resolution, sorry. So we show in painting, so that's in painting, so that's the observation, that's the original image, that's the image that we reconstruct, the image with DPS, and that's the image with DRM. Okay, so sometimes DPS get completely crazy. Okay, so we have this observation, look at that, DDM. So we have a lot of examples like that. Okay, it works very, very fine. And in fact, this divide and conquer use basically, as I said, two types of approximation. It uses both this decomposition and Feynman-Kalk, but it's not pure. It's in fact, you might see, as I said, in Feynman-Kalk we guide the diffusion with artificial potential all the time. In DCPS, in fact, there is a way where we use a bit DPS in order to construct this artificial potential. So it's a kind of okay. So this is one possible technique. As I said, there are a lot of open problems there. So we don't understand much how it works. We have methods. We are still trying to make methods which works, which are we want to have methods which are robust to the choice of hyperparameters. And so if you're interested, there is a paper in EURIPS. So we submitted yesterday. So it's fresh from the oven. We have codes. We can share codes. Yes, that's it. Thanks a lot for your attention.
Thanks so much, Eric. We have time for a couple of questions if somebody wants to ask something.
Thanks, AJ. Thank you, Eric. So just a question about sort of the basic framework, not the conditioning.
Okay.
So this is essentially a transport problem. You start with some unknown distribution, and transport its mass to pi ref, right?
Yeah, of course.
And you use some ergodic process to do that.
Exactly.
And now errors are driven by the amount of time it takes to do this transform.
Yeah.
Because you have to approximate, you need to do.
Yeah.
You want to have this t as short as possible. And in the beginning, your model setup was such that you could, in principle, use many different diffusions, right? Even to hit a Gaussian.
Yeah, of course.
Right? Are there any results
that
tell you that what you do with the OU is actually optimal in some sense?
No, there is nothing optimal. In fact, people doesn't. For example, if you use this to speech signals or music, you will not use. But in speech signal, for example, if you take frame of speech, it's harmonics. Okay, so which means that you have the spectrum, which you have some energy where you have the harmonics, which are where they have a lot of power. So other part which is where you don't have power. So of course, if you don't put white noise, you put a noise which is adapted to the signal. So no, it's not always. So people typically use Gaussian diffusion, okay, but with in general not sometimes diagonal covariance. So it's very, very. So no, there is nothing. There is nothing special of using non-diagonal. And if you are only interested in, of course, also if you are only interested in sampling, people use in fact what they call the correction stuff. So what you do typically is that, of course, you don't sample exactly the target. So you stop. So the first idea is that either you go really to the end. Okay, if you go really to the end, it will take a lot of time because you need to destroy all the structure of the signal. Now you can stop earlier. Okay, and of course you still have some relevant data information there. It's no longer exactly Gaussian. It's simply the pi data which is convolved with some amount of noise. And what typically people do is that they run a Langevin. So the way that you can sample, in fact, exactly the distribution pi t, because you estimate in this step, you estimate always the gradient of log of pi t. So you can use the Langevin, for example. So which means that you draw a sample from the data distribution, okay, and you add the right amount of noise, and you start to. That gives you a kind of sample, an original sample with noise in this after the t step, so it's noise, and then you start run some step of Langevin diffusion there. And when you have run some step of Langevin diffusion at time pt, you go back to time 0. It's called, they call that a prediction correction scheme. And so it has been analyzed. So there is a ton. There are a lot of, so in the case of diffusion, so without conditioning, there are tons of results. So Wibisono, Shui, so there are a lot of people which have worked on this area. Sabanis, for example, with a student.
But I was thinking about spatial inhomogeneity in sigma.
Yeah.
Because you know, in the Langevin case, when you run Monte Carlo, sometimes if the target is heavy-tailed, it's a good idea to have unbounded variance. Because you converge fast. Maybe this is also the case here. Is there anything that says that this is not the case?
No. So of course, this would be interesting. I know that people have looked at Evitel. I'm not sure where it has been. People have started to look at how to use that with Evitel stuff. I don't work at all on this area, but I think it's interesting. But because the thing, what people have looked at in general is more the case where pi data is satisfy a log-Sobolev inequality, something like that. So it's nothing with Evitel. So it's like, and then we adding Gaussian. So Sabanis is even worse than that. So Sabanis is assumed that pi data is strictly log concave, for example, which is completely realistic. But okay, so what happens next? Then people, so if you look at Wibisono, they did something where they assumed that pi data satisfy a log-Sobolev inequality.
But here it's multimodality that drives everything. I mean, it's not this.
This way it's a kind of art, you know. So you need to have some kind of
Do you have a continuous time diffusion context for this conditioning also?
No. So I used only discrete.
But is there something?
Yeah. So I used here. It's always, in fact, implementation people use only discrete time, of course. So there is no discrete time, but nevertheless a lot of time steps. So what people? So in fact. Something which is also very, very if you are a user of ChatGPT, you are a user of ChatGPT. If you are a professional user of ChatGPT, you have access to DALI, and it's very long. If you generate image, it's very long to generate image. Why? Because they are using diffusion. It's what they call stable diffusion. So it's a diffusion. They use VIE, so they use a kind of vector encoding. So it's not they are not using a diffusion on the pixel space. They use a diffusion on a kind of feature space. So they learn by a kind of Bayesian autoencoder, so a huge one. But the time which it takes a lot of time because they sample the diffusion is sampled with a lot of time steps. And what people, in fact, if you look at the literature, there are many works on how to sample this diffusion with much fewer number of time steps. And so mixing with ODE, and there are tons of papers like that. Okay, so if you are, and people, and in fact, surprisingly, tricks which are known by SDE people who are useful there. So in fact, they use integrators, they use smart integrators of the SDE. So in fact, it's if you are because you are an expert in numerical of SDE, you can be a millionaire, guys. It costs so much, you know. So in fact, if you look the investment of Microsoft, they invested. They say, okay, in 2 years we will buy $100 billion GPUs cluster, and they will buy a kind of nuke power just to yeah, it's true. Huh? So it was announced yesterday. So it's 1/3 of the budget of France. So it's but Microsoft capitalization is more than the gross national product of France. So even in here, I think it would be people with. It's like okay, so we have to do something. Either we build Neon or we buy a kind of supercomputer to run of this model. But I think it's a tough issue. So in fact, the sampling fast this type of diffusion is tough. And I think diffusion are more. In fact, there is also something which is very interesting. I'm not an expert of that, but so right now the LLM are based on autoregressive simulation, and but people start to they have noticed that you can of course use diffusion to sample jointly discrete distribution over large state space. So they are okay. You should not add noise. You should do something else. You need to do something else. But diffusion seems to be more promising than than autoregressive. So because in every, for example, when you look at the history of image, people use autoregressive model like pixel CNN and things like that. So they use a kind of to do an image with you define a kind of path in the pixel space, and you use some kind of autoregressive process along this pixel space. And in fact, diffusion now, nobody does that. Pixel CNN has completely disappeared, and people use diffusion. So people say, oh, if for image diffusion do better than autoregressive, they also should do better for example, some task where you have this, for example, language, where you have discrete number of tokens, huge but discrete. And what they have observed, it's true, in fact, on some tasks, in fact, they do better than classical autoregressive LLM. So you have diffusion in discrete, for example, for coding, they seem to be much coherent than LLM. So I think there are a lot of things to work in this direction. And of course, as I said, insight from people in numerical SDE can be useful there. And if you look at, so they use Runge Kuta, so they use even behind the scene of OpenAI, they don't use naive methods, and they are very rich.
Thank you so much for that very long and interesting speech, Eric. I think we're out of time now. Let's thank Eric and both speakers again. Thank you. So we resume at 1:30. The speaker is Nadir Ben Rashed, and the chair is Alex Mijatovic. Thank you.